magnetic materials. And we have 4 talks, 2 of them invited talks and 2 contributed talks, running through to the coffee break at 2:30. As Tom said, for questions, if you put them in the chat or raise your hand, and I think you can put them in the chat at any time, and then we'll handle the questions at the end. Okay, so our first speaker is Professor Torsten Hesjedal from the University of Oxford, who's going to be talking to us about magnetic skyrmions studied by resonant elastic X-ray scattering in transmission and reflection. So over to you, Torsten.
Well, thank you very much, Elizabeth. Let me just try to get everything to work here. Just a second. All right. Can you see my screen?
I can see your screen. I'm not sure. It looks like it's slightly cut at that. That looks better.
Looks better? Okay.
I think so.
Wonderful. And you see my laser pointer as well?
Yes.
Okay, wonderful. Well, first of all, I would like to thank Tom and Anne for organizing this conference. I mean, this enormous effort they put into that in these difficult times. And I really would like to be in Lund, but well, now I'm in Berlin on beam time, and I'm talking from here. Okay, so let's dive in. So I would like to give you an overview of, first of all, magnetic skyrmions, and then show you what and how we used X-ray scattering to unlock their secrets and study them in greater detail than is possible with any other method. Let me start by thanking my collaborators, especially from the early years here. Most importantly, Shilai Zhang, who's now a professor at Shanghai Tech University in Shanghai, and Harriet Vanderlaan from Diamond and his group, especially David Byrne. Okay, so I'll start with an introduction to magnetic skyrmions, what they are, which materials host these wonderful objects, and then also what we can do with them. Okay, so here you see actually a magnetic skyrmion here. So that's a kind of a vortex-like structure. It's a magnetic whirl of the moments shown here. And if you if you go backwards in the projection, in the stereographic projection onto order parameter space, you see that every direction is represented here, and they're all normal to the surface of the sphere in order parameter space. So that's a type of skyrmion. The key point is that these skyrmions have a non-trivial topology, which means that the magnetization pattern cannot be continuously or smoothly deformed into the magnetic ground state, which is the state in which all spins are aligned. So we represent that by a coffee mug that cannot be deformed into a sphere here. It all started with a paper on cubic magnets. So it's a theoretical paper by Bogdanov and Jablonski in '89. These are cubic magnets without inversion symmetry, and I will show you in a moment what this is good for. Then it resurfaced in the context of quantum Hall systems shortly thereafter, and then finally in 2009, Christian Pleiderer's group in Munich, using SANS, demonstrated that there are magnetic skyrmion lattices in manganese silicide. So in systems in which the inversion symmetry is broken, you can, apart from the symmetric exchange interaction, also get an antisymmetric exchange interaction, the so-called Jaruzelski-Maria interaction, which favors actually tilting or twisting of the spins, which gives rise to, for instance, the helical state here that is shown here with the propagation vector QH. So skyrmions can be seen to first order, so this is a simplification, but good enough for the discussion here, as a triple Q solution, so 3 helical orders put together, forming this hexagonal skyrmion lattice in 2 dimensions. These non-centrosymmetric crystals in which skyrmions were discovered, these so-called B20 crystals, have a universal phase diagram. I put the word universal in parentheses because much more has been discovered about the specifics of the phase diagram. So let me just focus here on the key points. So the key point is that below a transition temperature at a finite field, you get the skyrmion pocket. This skyrmion pocket requires this rather high temperature for the system because it's a fluctuation stabilized phase. Apart from that, at zero field or small fields, you have the helical phase. Above the critical field transitions into the conical phase, and then finally at a second critical field into the field polarized state. The energetics of the system is determined, but first of all, by the Heisenberg interaction, followed by this by the Jalutinski-Maria interaction, and finally you will observe crystal field effects that determine the locking of, for instance, the helical state into crystallographic directions. In the third dimension, to first order, the skyrmions, which are 2D objects, can be simply seen as a stacking up of this pattern. So the skyrmions form, in fact, tubes in depth, like here. So in which systems do skyrmions appear? Well, first of all, non-centrosymmetric crystals, as I mentioned. So this would be, for instance, the B20 crystals. Examples are silicide, iron, germanium, and here is shown iron cobalt silicide to give you an idea. Another area in which skyrmions were discovered are systems that are characterized by spin-orbit coupling and structural inversion asymmetry. So this would either be surface systems. That was worked by Wiesendanger's group in Hamburg with a spin-polarized STM that discovered that. And much closer to my heart is a thin film Persona interfacial system. So this is coming out of Albert Ferd's group. Here at the interfaces, you also get a DMI, and you can nucleate skyrmions in these heterostructures. So how do the skyrmions look like? Well, there are different flavors. First of all, there's the Bloch type skyrmion. The name is coming from the appearance of the domain wall, essentially, if you cut through the skyrmion here. These Bloch type skyrmions appear in, as I said, B20 materials, but also copper oxyselenate and cobalt zinc manganese. Another type of skyrmion are nail type skyrmions, and quite fittingly, these are the skyrmions that appear in Albert Ferd's heterostructures, so interfacial system, as well as gallium vanadium sulfide. And more recently, the zoo is getting bigger and bigger. There are skyrmions, and then like anti-skyrmions here, and as well as hopfions and so on. So these are higher order modes. So what are the advantages of skyrmions? Why are we doing this? Well, compared to spin transfer torque induced motion of domain walls, the required current densities are several orders, in fact, more than 6 orders of magnitude smaller. So the manipulation of skyrmions gives rise to this proposal of a racetrack memory type scheme. The other thing is that topology usually sort of suggests that it's somehow protected that state. And so there's the hope that this helps to overcome the superparamagnetic limit of miniaturized storage bits. And in principle, you should be able to look at skyrmions or use skyrmions down to a nanometer in diameter. So that's quite attractive prospects. Okay, so how do we look at skyrmions? So we are using resonant elastic X-ray scattering in the soft X-ray regime. So first of all, we do what everyone does with a real space imaging technique, but in reciprocal space. So this is the diffraction pattern in the helical state. You can see this 2 Friedel pairs, in fact, one that you should be seeing quite easily, and then a much fainter one. So what this is 2 helical domains in the system, which you obtain at 0 or low field. Then if we crank up the field and we transition above the critical field into the conical phase, we get our 2 conical peaks that are aligned like that. And then finally, if we increase the temperature and raise the fields to be in the skyrmion pocket, we get the 6 characteristic peaks stemming from this hexagonally ordered skyrmion lattice as shown here. We can then also scan the sample in the Rex configuration and tilt the field, and what we get then is the formation of in-plane rotational domains. So shown here in this plot on the right is if we introduce an azimuthal rotation angle psi, you can see the rotational domains here ranging from, say, 10 to 100 micrometers or hundreds of micrometers in size. Okay, so far that's sort of a bit boring. I mean, we are able to map out the phase diagram, and we are complementary to all the imaging techniques. But the problem is with most imaging techniques is they don't really have the lateral resolution to look inside the skyrmion, determine its flavor. It sort of works in Lorentz transmission electron microscopy, but only in a very indirect way. And also there's more to it. That is the so-called topological winding number. So here I give a quick introduction to the so-called dichroism extinction rule that we use for the microscopic investigation of skyrmions. Again, let's start to look at this triple Q construction. Underlying there is the so-called characteristic helix that is characteristic for the skyrmion. So we're going to look at that in more detail. And so what we introduce is the so-called common rotation plane. This is the plane in which our moment rotates as you go, for instance, along the cycloid here or along the proper screw. Note that there's an additional angle chi, which is the helicity angle, and which essentially describes the rotation of the plane in this propagation direction. But we can also have any angle. So this is shown here, one at 60 degrees. And so we determine here the complete orientation of this plane in space. We can also apply a field and then extract the conical angle as well. How do we do that? Well, we do azimuthal scans about the Q vector. It's shown here. Okay, so now I will show you a sequence of images. What you see here in yellow is the sample. There's an illustration of a helix. Gray is the scattering plane. And the bottom left, you see a plot of the MZ component of the magnetization distribution in the helical state, in this ordered helical state. And the bottom right-hand side, you see the two diffraction peaks with a small twist. And the small twist is that this is a dichroic diffraction peak plot. So what we do is we subtract the intensities obtained for the two opposite polarizations. And so we have here, in this case, a positive diffraction peak and then a negative diffraction peak. Okay, let's start rotating. So as we rotate, we notice that the peaks, of course, follow the orientation of the lattice. So that's nothing new. But you can see that these peaks in the upper half, defined as above this line here, are yellow, meaning positive. And in the lower half, they are negative, meaning blue. So we can rotate that further. And we see how this evolves. So if we have a helix with a chi of minus 90 degrees, what you will see is a dividing line between positive and negative contrast that looks like this. If it would be plus 90 degrees, the colors would be inverted, and blue would be on the left and yellow would be on the right. Okay, and this is an example for chi equals 0 degrees. That would be a horizontal line. Well, of course, from two diffraction peaks, it's hard to determine. So if you would have a polycrystalline magnetic material, so to say, you would be expecting a ring, and this ring would then have a clear separation between positive and negative dichroic contrast. Okay, and in order to describe this properly, we can write up the equation for the dichroic intensity as a function of the azimuthal angle psi. So as we go around this ring in intensity, this is proportional. Let's ignore these constants here for a while. It's proportional to the sine of psi plus this offset angle, which is the helicity angle, this rotation of the common rotation plane in the helix. Now we carried out a measurement on carboxyselenate, and you see here the four peaks in the helical phase. Again, there are two domains perpendicular to each other, locked along crystallographic directions. And you see here then the dichroic peaks, which are positive here on the right, negative on the left. Then through rotation, by the fact that we have four peaks, we can then plot these intensity values like so and fit it with the sine wave, and from that extract the angle chi. And in fact, we extract an angle of 90 degrees, which is what we expect for the helical phase in carboxyselenate. We can also do that in the conical phase, and what is interesting there is that we can extract the cone angle, and you see as this is the plot of the cone angle of the magnetic field, and you can see as the field is increased up to the transition point, the critical field, the conical phase transitions into the field polarized state. So that is what we can extract out of that as well. Now, how does this helicity angle actually work together with the skyrmions? And what I've shown here is an order parameter space. First of all, is this hedgehog structure. So you see that the spikes are all perpendicular to the surface. And if we project that down through stereographic projection, we get the real space magnetization distribution in the skyrmion, and this would be a so-called nail-type skyrmion. There is also the possibility that you have a smooth deformation of the moment. So you kind of comb it in one direction, which is allowed. So we're not changing anything on the topology. It's just the flavor, so to say, of the skirmion we change. If we project that down, we get a so-called block type skirmion. And this is what you would really like to measure. Okay, and so classically, in the literature, there were usually only two types of skirmions reported. There was the Bloch type skirmion with the chi of plus or minus 90 degrees, and the Nail type skirmion with chi of 0 or 180 degrees. If we look into the equations of the magnetization components in the skirmion, we see that the in-plane components M1 and M2 contain this helicity angle chi. M3 doesn't. Okay, so the dichroic extinction rule is really the observation that if we look at this plot of the dichroic intensity, we can see that this separating line, which is in fact a vector because we separate positive from negative in an orientation, has a one-to-one correspondence to the helicity angle as shown here. So the helicity angle really is kind of a skewing of this in-plane orientation or rotation of the magnetization components within the skirmion. What we came up with out of this is a skirmion clock. In the skirmion clock, you can measure this extinction condition and from that conclude the chi. So what you would expect for a Bloch type, for a B20 type crystal system is Bloch type skirmions. So either minus or plus 90 degrees, that depends on the chirality of the system, meaning if we have a left or a right-handed crystal. Now we carried out the measurement in copper oxyselenate, and what we find is that for the left-handed crystal, we get a chi of minus 128 degrees, and for a right-handed crystal, we get a chi of 100 and plus 129 degrees. So this is matching, however, it's not 90 degrees, and I will talk in a moment about what's behind this. The other thing, just briefly to finish that, is what we can measure is the so-called winding number N. So the winding number is also encoded in the magnetization components of the skirmion, and it really describes on how often you have you can map the skirmion structure onto the sphere in order parameter space to catch all the moments in the skirmion. So if you think about an N equals 1, so winding number 1 system, where you wrap it exactly once, we can deduct that from the zero crossings here of our dichroic intensity here shown as a pseudo 3D plot. And these are higher order skirmions, so N equals 2, 3, and 5, etc. And see, this is kind of an N equals 2 system, which looks quite knotted. And the way to decipher that is you can think about cuts through the system where your domain wall would have 2 windings essentially in the skirmion system. If we carry out the measurement in copper oxyselenate, we indeed get a winding number of 1, which is to be expected. So what this dichroism extinction rule helps us doing is, first of all, we get the helicity angle, we can determine the winding number, and also the chirality of the system. And furthermore, of course, analyze the full spin spiral. So what have advanced REX techniques, what do they have to contribute in order to be useful in this context? Well, first of all, we want more spatial information. We want, in fact, to visualize the magnetic structure 3D. And also, we would like to have time resolution in the system. I'm getting some noise there from somewhere.
Tom.
Okay, I'm just going to move on. I think now it's over. Apologies for that. Okay, so so now we're going to show you what we can do in terms of a sort of tomographic mapping of skirmions, so the 3D structure of skirmions. What's behind it there is that, in fact, the sampling depth is a strong function of the energy across the L2, L3 absorption edge in transition metals. So we can go on edge from about 30 nanometers to closer to 130 nanometers if we are off edge. And we still get a decent diffraction signal. So here is a plot of the measured chi, so the measured helicity angle as a function of energy, and we can decode that and get a plot of the a plot of this probed chi as a function of sampling depth. The interesting thing is to note that none of the angles are actually 90 degrees, but the uniform Bloch skirming would be down here. That's what you would expect. But we measure a different value, and it's closer to 180 degrees at resonance, and it's closer to 90, closer by a bit, of resonance. Okay, so if we do this plot of the probed chi over the sampling depth, we have a behavior like this. The free fitting parameter that we used is of course the shape of this curve, as well as the surface value of chi. What we nailed down was that deep in the bulk, we insist that this has to be Bloch type skirming with chi equals 90 degrees. And then we do a model where we slice the thing and integrate up the intensity, and we get a so-called then probed chi as a result of this sampling. And then you see that there's a surface twisting of the skirmers, and in fact, on the surface, it's nail type, even though it's a non-centrosymmetric bulk crystal. So it's a nail type system, and the decay is quite deep. So it goes up to hundreds of nanometers deep into the bulk before these bulk values are reached. So the surface is very important in this fine energy balance for skirmions. What we're also interested in is internal skirming dynamics. So skirmings can be excited to have, for instance, counterclockwise and clockwise rotations, and for instance, breathing modes. And what you use for that is ferromagnetic resonance, which of course doesn't give you any modal information unless you do simulations. So what we wanted to do, and did in fact, is to combine FMR with the REX technique to unlock the complex dynamics. And we published 2 papers on that in 2020. One where we combine it with REX, and one where we combine it with refractometry. And so we can look at the essentially at the time dependence of the diffraction spots, and draw conclusions out of that in terms of the dynamics of these various modes. Okay, so the issue if you do reflection REX is that because we're looking at an incommensurate magnetic order, there are magnetic peaks that are decorating the structural Bragg peak. And the structural Bragg peak can be nicely reached in copper oxyselenate, but not in many other systems because their lattice constant is simply too small. Then it's transmission REX to the rescue. And here you see an example on iron germanium. So iron germanium was cut out as a lamella. This is done in a technique that is used for transmission electron microscopy normally. And here you see the helical structure. So this is really polycrystalline helical order. And here you see the skirmion order with your characteristic 6 peaks. What we've used it for is to look how to measure, in fact, the so-called skirmion Hall angle. This is an interesting feature of skirmions in the fact that their topology gives rise to a Magnus term in the equation of motion, meaning that if you drive the skirmion in a certain direction with an applied force F, it moves in another direction. And the angle between the 2 directions is called the skirmion Hall angle. Which is easy to measure if you have single skirmions. So in heterostructures, you usually have single skirmions. That's easy. You pulse them and you observe them where they started off from and where they end up in, and then you can kind of trace them, do statistics on that. That doesn't work for lattices. So what we've done, we attach an Ørsted wire. In the Ørsted wire, we create a linear field gradient. Here are several systems shown with different increasing skirmion Hall angle. And what you get is a shearing of the lattice. So we introduce defects and your diffraction spots elongate, and the whole lattice rotates. So you get a rotation into place and an elongation. Out of that, you can determine uniquely the skirmion Hall angle. So first of all, if we switch on the Ørsted field, the whole system goes from a multi-domain state into a single domain state. And if you then analyze the peaks clearly and you look in which direction they actually deform, so where the strain builds up in, you can conclude the skirmion Hall angle for iron germanium, for instance, to be 55 degrees. So in the last minute, I just want to highlight another method. This is grazing incident REX. So again, if you have an issue not reaching the structural Bragg peak, you can also measure REX and grazing incidence. This is some preliminary data on manganese silicide again, but now bulk crystals. So there's no preparation needed. The preparation of lamella usually has a big problem if the thickness of the lamella is on the order of the skirmion characteristic length scale. you have confinement effects. And these confinement effects screw up the phase diagram determined by a grade fraction. So it's still meaningful data, but certainly not equivalent to the bulk data. So this is different in grazing incidence. This is just a very brief overview. I want to show you of some data. So if you apply, first of all, a field, these Skyrmine cubes follow the field inclination angle. This is the helical phase shown here, the Skyrmine phase, and the conical phase information in grazing incidence. And then what we do is we, as I said, change the angle. And what we do this way is we cut the Skyrmine lattice in various ways. And we combine that with a change of the incident angle. That means we probe various depth, and in the combination of the two, angle and incident angle and field angle, we can reconstruct the whole 3D Skyrmine lattice as a function of depth in these systems, but not requiring any special surface preparation. Good. Let me quickly conclude my talk. I would like to make some advertisement for the book that Shilai Zhang wrote. This is his thesis, essentially. If you want to read up, then have a look here on the Springer thesis webpage. So what I hope I was able to convince you is that resonant elastic X-ray scattering is a powerful tool for the study of Skyrmines, going way beyond just their presence in first-degree order. I showed you how you can determine the helicity angle in these systems and kind of determine the Skyrmine flavor this way. I also showed you that the 3D structure of Skyrmines and the fact that the helicity angle is in fact not just 90 or 180 degrees in these systems, but it's a continuously varying function that can be easily altered by the presence of additional energy terms like in the vicinity of a surface. Transmission racks is also important and can be used for an extremely wide variety of samples and materials. The issue there is that you get confinement effects. However, it's still interesting to do because a lot of real space techniques like Lorentz TM or Stixon, of course, work with the same type of samples. And in fact, we did experiments on identical samples to get complementary data sets. And then finally, grazing incident racks is a more recent method for us. And it's still being worked out, all the details. So there are a lot of little surprises, and then you can go even beyond what you can do in transmission racks. And it doesn't require any special sample preparation. Well, with this, I would like to thank you for your attention, and maybe we have another of these meetings in Oxford one day.
Thank you very much, Elizabeth. Share my screen. Can everyone see this fine?
It looks good.
Okay, great. So I'll begin. Thank you again, Elizabeth, for introducing me. I'm Peter Mills. I'm a PhD student at the University of York, where I'm supervised by Vlado Lazarov, and I'm working in collaboration with Stuart Cavill. And this PhD is also in collaboration with the Institute Laura Langevin, where I'm supervised by Thomas Salbreck. So in my project, I'm working mostly with ferrite heterostructures, and my main probe is polarized neutron reflectivity on machines such as D17, pictured here on the right, or also on SuperAtom. Okay, so I just told you that I'm working with ferrite heterostructures, and why are we interested in ferrites? And it's mostly because as materials, they can offer a broad range of magnetic and conducting properties, and in conjunction to this, they also have generally the same crystal structure, and so we can combine them quite easily. And so with that in mind, I want to introduce you to two ferrites. First of all, nickel ferrite. So this material presents large exchange splitting. We can grow it to be insulating or conducting, and it's a soft ferromagnet. In contrast, if we change just one element and we go to cobalt ferrite, now we see this material has a large cubic magnetocrystalline anisotropy. So it's a hard ferromagnet. It has high magnetostriction and low conductivity. Okay, so we see some interesting properties of these materials, and I already said to you that we're able to combine them because they have the same inverse spinel crystal structure. And also due to this crystal structure, it has many degrees of freedom, and so if we are able to slightly manipulate the structure by, for example, an effect such as strain, we can actually modify the physical properties of these materials. So with that in mind, what we wanted to do was grow NFO and CFO as thin film heterostructures on a highly lattice mismatched substrate, in this case aluminum oxide of around 8%, and we wanted to investigate how the physical properties will be modified by effects such as strain or magnetic proximity effects. Okay, so we need to be able to see magnetization across chemically different layers as a profile of depth on the nanometer length scale. And so in order to look at this, we employed a technique called polarized neutral reflectivity. And so this slide is just going to be a quick introduction to the technique. So for all of our measurements, we were taking them only in specular conditions. And so this means that our angle of incidence is equal to our angle of reflectance, and our momentum transfer will be normal to our sample surface, meaning that we're probing in the Z direction into our sample. And so now we can take a look at what a measurement might look like for this technique. So on the x-axis, we have our momentum transfer, QZ, and on the y-axis, we have our reflectivity. And so in blue, we see a reflectivity profile. And this profile is nothing but the interference of waves which have been reflected from the surface and the interface of our layer and our sample substrate. And so if we wanted to model this reflectivity profile, all we need to do is treat this sample as a potential well and use the Schrodinger equation to solve its boundary conditions. And so normally we consider the height of the potential well to be equal to the scattering length density, and this is just the number density of the layer multiplied by its the sum of its neutron scattering lengths of its individual elements. Okay, so if we try to model this data, we might get something that looks like this. Okay, so we see on the x-axis we have Z depth into our sample, starting at the substrate, and on the y-axis we have SLD. And so we can see here the SLD of our substrate. Then we go up into our sample, and we leave our sample. And so we can see the different SLDs of each layer, and we can also see the thickness of our sample on top. So this is great, and this is two of the things that we're going to need. But I also need you to know that neutrons have a magnetic moment, and this magnetic moment can interact with the magnetization inside of our sample. And so if we want to see, for example, the projection that this magnetization makes in the direction of propagation of our neutron beam, what we need to do is measure two states. We need to measure parallel to our applied field and anti-parallel. And if we were to do this, we see a reflectivity profile that looks like this. So we can see our parallel state here and an anti-parallel state here. And by modeling these two reflectivity profiles, we're able to tell this projection of the magnetization in plane. And so we can say that we're sensitive to the magnetic moment density, or the MSLD. Okay, great. So with sensitivity to layer thickness, nuclear SLD, and magnetic moment density, or MSLD, we should be able to see all of the properties of our bilayers that we're interested in, or most of them. Okay, so next I want to show you one of the experiments we did. And this experiment was performed on a sample NFO 25 nanometers, so N25, CFO 26 nanometers, C26, and all of the measurements I'm going to show you performed at 5 Kelvin. So before performing PNR, we used vibrational sample magnetometry. Basically, we put our sample inside of an applied field, and we measured its magnetization. And so the procedure for this measurement was actually similar to what we did in PNR. We took our sample, we applied 5 Tesla, then we came down the hysteresis loop. We go to negative saturation, so somewhere around minus 5 Tesla, and then we come to this point here. And so I said to you at the start of this talk that we're interested in the changing magnetic properties of these individual layers. And so if we go to this region where our bilayer is magnetically switching, then we may be able to observe the individual switching of our two layers, and we might be able to observe any physics that might be happening at the interface between these two layers. Okay, so that's exactly what we did. I show you here on the right some reflectivity profiles taken at fields in this region, and also one taken at saturation, around 2.2 Tesla. And here on the bottom right, I show you the modeled SLDs from these reflectivity profiles. So starting from here, so here we have our black line is our nuclear SLD. We start at our substrate, and we go into a region of cobalt ferrite. Then we go up through a chemical interface into a region of nickel ferrite. And already this is one nice result, because the SLDs of these two layers were what we expected, are very close to what we expected, and so this means that our chemical composition of our individual layers looks good. Now I want you to look at this red line, and this red line was taken at 2.2 Tesla, so this is our saturation measurement. So starting from our substrate again, we go in, we see a region of cobalt ferrite, we see a gradient magnetization at the interface going down into nickel ferrite. And so what I've plotted in these dashed lines is, in blue we have the expected bulk value of magnetization from CFO, and in orange we have the expected bulk value of magnetization for NFO. And so we can see in our region of CFO that we're quite below the bulk value. So we see a reduced magnetization, and also in our NFO we see as well that we're below the bulk value or the bulk magnetizations of NFO. So both layers have shown a lower magnetization saturation in this bilayer than you might expect. Now I want you to look at this orange line below here. And so on this orange line, we've measured at this star here, which is at this point in the hysteresis. So our bilayer was negatively magnetized. And we see here on the MSLD that CFO has a negative magnetization. We see again a gradient at the interface, and we see NFO has a negative magnetization. Not so interesting. Then we go to 0.4 Tesla. We see now NFO has a lower magnetization. The interface still has a negative magnetization, but our NFO has magnetically switched and shows a positive magnetization. And so now we've seen this kind of state that we might have expected from a sample diagram, where CFO is sitting, CFO and NFO are anti-parallel magnetically, but we also see this sort of region of exchange coupling through the interface and extending slightly into NFO. And we see this trend continue at 0.75 Tesla and 0.9 Tesla, where we see CFO hit its switching field and NFO basically saturates. Okay, great. So our layer composition looks good. We've seen lower than expected magnetization saturations, and we see exchange coupling. And so now what I want you to remember is, again, at the start of this talk, I said that we were interested in the effect that strain plays on the behavior of these materials. And so we know that we expect the strain to be at this interface here with the substrate where the aluminium oxide is. And so now we asked ourselves what would happen if we change the layer order, i.e. we change which of the materials is actually strained. So we perform this experiment. Here on the left, we have N25, C26, so the sample I showed you before. And here on the right, we have a new sample, C20, CFO 20 nanometers, N19, NFO 19 nanometers, and again, all at 5 Kelvin. Here's a new sample diagram, and here's some VSM that we took with the sample on the right. So I've shown you this VSM. We know that there are some issues with it, with our measurement of moment. So I want you to ignore the values on the x-axis, but still remember the shape of this VSM. So that's what's going to be important. Okay, so now on the bottom right, we have our PNR on this new sample. Again, in the black line, we have our NSLD. So going up, we have a region of nickel ferrite, and we have a larger chemical interface here than on the sample on the left. And then we have a region of copper ferrite. Great, again, our samples looked good, the sample quality was good. Then we took a measurement at saturation, or around saturation again, at 2.2 Tesla. And so we see this here on our red line. So again, starting from a substrate, we go into nickel ferrite, where we see this sort of almost small gradient of magnetization. Then we see quite a sharp magnetic interface, and then we have a region of cobalt ferrite. And again, I've plotted the literature saturation values, and so we see that again, NFO is below its literature value, and the same for CFO. And now I'm going to add these black lines here to help you compare, because what we can do is we can look at the sample on the left, and we can take a look at the saturation value of NFO on the left, on the red line. And we see that it's lower than the value on the right, and we see the same for CFO, that at the peak here, this is a lower value of saturation than on the right. So it seems that by changing the layer order, we've changed the magnetization saturations of these two layers. Just interesting. And also, again, I want you to look at this orange line. So here is at the same point here on the hysteresis, and it's at the same field as the orange line on the left. And so we see that CFO is negatively magnetized, and that we have a slightly larger magnetization, negative magnetization on the right than on the left. And also, if we follow this line through into the NFO, now we see that not only are we coupled at the interface, but the magnetization has this gradient going all the way through NFO right to the substrate. And we see that this trend continues through to CFO. So we see here on the blue line at 0.4 Tesla, CFO again, a little bit more than on the left, negatively saturated. And again, we see this big gradient magnetization going all the way through NFO, where at 0.4 Tesla now, we see that NFO is at its coercive field. But at 0.4 Tesla on the sample on the left, that NFO had already magnetically switched, right? And so we see again the same trend going through to 0.75 Tesla and to 0.9 Tesla. So we've definitely seen some changing in behavior of the magnetic switching between these two materials. And what's interesting is you can actually almost see this in the VSM. And so if you look at the VSM on the right, again, just looking at the shape, it looks quite smooth and featureless. And this is what you might expect with this kind of magnetic switching, where we're seeing NFO gradually switch with CFO. Whereas on the left, we see that there's almost a sort of kink here in the VSM. We see a slightly more clear feature, and this is likely this NFO layer switching sort of independently in this region. And so this means that our PNR and our VSM is in general telling the same story. So in conclusion, we said that we wanted to grow bilayers of NFO and CFO on a highly lattice mismatch substrate. We want to see if their physical properties would be modified via things such as strain and magnetic proximity effects. We've seen in both of these samples magnetic interaction, a region of exchange coupling. And we've also seen layer order dependent switching fields and magnetization, demonstrating that strain plays a role in the behavior of these materials. Okay, so that's my talk. Thank you very much for listening. Please let me know if you have any questions.
Yes, who is going to be talking about magnetic correlations in triangular dipole coupled Ising spin lattices. Over to you, Arthur.
Thank you, Bridget.
Yep.
So I will report on a nice GSANS experiment that we published last year, and especially on how this allowed us to see what normally is very hard statistical correlations of magnetic moments in nanoscale structures, and how we modeled that. So first, about the system, frustration is being studied for quite a long time, especially in bulk systems. So the simplest form is where you have 3 spins on a lattice with an antiferromagnetic coupling, and so only 2 neighbors can fulfill this coupling. So there is some frustration arising from this, especially when there's just one neighbor coupling. And in bulk, you normally have this as an exchange interaction that comes in. But if you have dipole systems, it gets a bit more interesting as you get into long-range correlations, long-range interactions that somehow modify this simple frustration picture. And so there were some theoretical Monte Carlo simulations that showed that there's some kind of different phases where in the lowest temperature they actually order in some kind of stripe shape because of this long-range interaction. But if you distort the lattice in one direction, you lift the frustration, and so you can get this a bit more complex phase diagram. And we wanted to study this using a nanoparticle system. And in the different phases, the correlations starting from this long-range stripes start to get more randomized while still keeping the ice rule in the triangles. And at higher temperatures, you also get 3 up or 3 down triangles that are higher in energy. The samples we have prepared with a electron beam lithography over the whole sample. So you basically you start with a gold silicon and gold substrate, and then have a PMMA coated optical resist, then e-beam lithography, and then we use electrodeposition to grow iron nickel into those holes, and then removed the template with a solvent. And you can see these are the resulting patterns. So they're very nicely structured. And because it's an e-beam over the whole sample, the orientation of the pattern is the same everywhere on the sample. The experiment was done at Maria in Garching. And this is how the sample looked like at the holder. So we have the large silicon substrate, and the structured area is something like 20 millimeters by 5 millimeters. And the instrument is quite well suited for this kind of experiments because it has a relaxed wavelength resolution for a reflectometer and a specific GSANS mode with a longer collimation than most reflectometers, but also has very good polarization analysis capabilities. And this is really important if you want to study magnetic systems and get more information than just the correlations. Because we have this organized structure over the whole sample, we have to rotate the sample in the beam. And the rotation angle around the surface normal we call phi. And you see the geometries, we come in with a pencil-like beam, and then the grazing incident scattering is measured on a position-sensitive detector. And this planes that are parallel to the incident beam direction or almost parallel, they give us some bragg peaks here, and in this orientation, they are in Qy of 4p over square root 3 times the distance of the particles. Polarization was in plane perpendicular to the incident beam, and the structure itself was about 135 nanometer high cylinders. The A we call the closest neighbor distance between two cylinders. The magnetization, because of the shape anisotropy of the cylinders, is out of plane, and the diameter is about half the distance of the particles. And you can see here, this is a unpolarized measurement of a sample with about 70 nanometer A. And this image is a combination of several phi angles just added together. And if you look at these integration areas here and scan the phi angle, you can see that one peak is very sharp and the other peak is very sharp on the other side. And the specular peak actually loses intensity when we get on a scattering or on a bragg peak from the structure. So this shows we have very high structural quality, and we also could fit this structure and get correlation lengths of several 10 micrometers, which is limited by the neutron coherence of this experiment, actually. But this also shows that when we are on these bragg peaks, the scattering is so strong in plane that the assumptions of the distorted waveform approximation even don't apply anymore. But on the other hand, if we go here at phi equals 0, the structural scattering is really, really low. And as we expect the magnetic order to be a shorter correlation than the structural order, we can actually use this to suppress the structural scattering and get closer to the magnetic order. So then we also did polarization analysis measurements. So this is on a sample with a compressed lattice, 10% compressed in one direction. And here you can see this the spin up, non-spin flip, spin up channel, and the spin flip, spin down channel as measured and as simulated with a stripe-like structure with short correlation length. And this is how this order would look like. And you can see that it is relatively well described, but we see very strong magnetic signal, very strong relative to the other such experiments, I would say. But this is when we assume the spin out of plane. Now to check how this would look like with an in-plane spin, because we apply the field in plane, this would have been a possibility, but this doesn't fit the non-spin flip channel, and also in the spin flip we have deviations. So we can say that we have confirmed that there's an out-of-plane anisotropy as expected. And we also made that experiment with a symmetric lattice of about the same lattice constant, but we find that there's still strong scattering at almost the 1/2 position, but the shape of the peaks does not fit at all what we would expect from having just 3 stripe domains coexistent. So the question was how to what is this kind of order we have, and how can we describe this? So to explain this, we start from how to model such data. So as in other scattering experiments, you can build a structure factor that is made out of the nuclear structure of this long correlation lattice, as well as either the long range ordered stripes or some kind of short range order. You have then to add the form factor of the cylinders that change the Q-dependent intensities, and also add the magnetization distribution and strength to the system. This can be plugged in to a DWBA modeling. Here we use the Born Again software for that. And also we add the layer structure, because this at grazing incidence has a strong influence on the intensity distribution. And finally, we add all the parameters from the experiment, the geometry, the resolution of the beam, the detector size and distance, and so on. So how to describe this structure factor of such a system? There are theoretical predictions with the Monte Carlo simulations about how the structure factor of the spins itself should look like. And those are in the lowest temperature just the stripe. And this is we could already describe with a normal born-again models. But in the higher temperature, these are statistical averages of all those spin orientations. And there's no analytic formula to describe those directly. But we also cannot add this one-to-one into born-again from because we want to fit our data to it. So our solution was to come up with an empirical structure factor that describes this kind of behavior without having too many parameters to model our data. And this structure factor will then be plugged into the model. And this is made up of the short range stripes that have two correlation lengths, as well as what we call the tri-state peaks. And those are the parts that cannot be described with a normal modeling in born-again because they have some kind of triangular structure. And all other cluster forms you would build up in those models would be six-fold symmetric and not three-fold symmetric. So this we added as a customized structure factor. And then we wanted to reduce the number of parameters as we have all those chi parameters here. So we fitted those to Monte Carlo simulations of the different temperatures. And this is how this looks like for the symmetric lattice. So first we fit every single temperature that was modeled in Monte Carlo individually. And then we made up a model with more smooth parameter variation that was then globally fit to everything. As you can see here, the continuous lines. And then compared the Monte Carlo model with the structure factor, the analytic structure factor. And as you can see, the differences at different temperatures are very low in the order of a few %. And the same was done for the distorted lattice, which is a bit more complicated to describe because the distortion also distorts the shape of the peaks in the unit cell. But even there, we get relatively good agreement, still below 4% of deviation here. In the very highly correlated area, it's a bit bigger, 6% deviation. And then we had the whole model has only one free parameter, the temperature, the Monte Carlo temperature. And this we fit to our data. And we co-refined the 2, 0, and 90 degrees orientations of the sample for the symmetric and distorted lattice. And you can see here the cuts through the Yoneda line that have been fit, and the model fits the data very well. And these are the structure factors that came out of the fit. And then we used the fit results to also model the polarized measurements, and those agree very well without any modification of the parameters. So from that, I hope I could show you the possibilities that you can do with GSUNs now also for diffuse magnetic order in these systems if you have the right samples. But it's really difficult to model this correctly, and I think we need to improve the options in the modeling to allow more complex structures to be displayed. We will do follow-up experiments, especially looking if this order is dynamic or static. And we will also try to improve on the modeling, considering the high scattering that we have in the from the long structural coherence. And with this, I thank you for your attention.